less than 11. And there's a question for you to think about related to the application of right-hand rule. And I'm going to use this question. Doesn't sound right to me. I'm going to use this question to talk again in general, to review what physics is about. Yep. And so as you know, we humans have two halves. One half of a brain can think about question, and second half of a brain can think about this stuff. And interesting. When I left, it wasn't like this. This room has some ghosts. Well, anyway, that's exactly what I wanted to do. You know, physics, learning physics has stages, the same stages as doing physics. And when we do physics, the first thing we do, we look, and wherever we find interesting, we name it. Naming is not a part which requires thinking, right? Naming requires memorizing. That's compass, that's magnet, this is wire, that's another wire, that's power supply. Then we'll look at them and we see something is happening, and we name important processes, rotation, and thinking only required when we need to connect the dots, when we need to explain what's happening or predict. Two reasons, explanation or prediction. So how can we explain this behavior? We know magnet exerts a force on another magnet. Each magnet has two poles, and like poles repel each other, opposite poles attract each other. But now we also can apply more sophisticated reasoning. We can say magnet exerts, generates, creates magnetic field, and that magnetic field now makes these magnets move. What is the direction of magnetic field according to a definition? Well, if we have a bar magnet, magnetic field lines travel away from it, go back into the south pole, out of the north pole, into the south, and at every location of another magnet, magnetic field is described by the direction from south to north inside the magnet. So this line, which goes out of this north pole, should travel here in that direction, and that direction from south to north. That's how this magnet should well, move itself. Choose orientation according to magnetic field at the location of it. And now we also know that electric current generates magnetic field, and that magnetic field, according to this rule, related to direction of the current. We also know the battery or power supply provides electric current, which travels from the positive high potential electrode like this and like this and then like this, and electric current goes into the negative grounded low potential electrode. So you see how many things we need to connect if we want to explain or predict in this situation. I want to predict what might happen with these magnets if I turn the current on. And well, this rule tells us what should happen. I should, well, if I have that physical ability, I can grab it, or I can imagine that I'm doing that, and my finger should point, the thumb should point in the direction of the current. So current begins here, travels that way at you. So from your perspective, current points at you, and from your perspective, magnetic field lines should, well, be circular like this relative to you. This direction has a special name relative to you. How do we call it? Counterclockwise. So if one asks you what the direction of electric field about this wire, you should say counterclockwise from your point of view. So what does it mean? It means below the wire, magnetic field points, how do we call it? To the right. But above the wire, the same magnetic field should point to the left. And this wire should make these compasses move. Yeah. These are less frictional. Here, if I move it closer, we can see magnetic field makes these compasses move. And if you see, oops, and compare the orientation below a wire and above, it's opposite, white to red, and here it's opposite, because magnetic field above and below are opposite. Now, this is just for one wire. Here we have 4. So all we have to do is just, well, repeat the same reasoning 4 times. For that, I can switch back to my computer, hoping it's going to work. So it is a good experience, a good practice to do it one by one. So we start from wire number 1. Wire number 1 is here. All right. This is a direction which we call out. So you have to imagine wire, like in this example, pointing at you, and current travels directly toward you. So as we just said, relative to you, magnetic field lines should be circular with direction counterclockwise. So we can draw a line like this. That's what counterclockwise means, counterclockwise. But the magnetic field vector we need to analyze is supposed to be drawn here. That's the origin. So what do? Well, we use our imagination. We extend, well, magnetic field lines are everywhere. Yeah. Those are circles. That's why we need imagination. Oh, I missed the point. All right. I moved the point. My point is, this doesn't work now. Nope. So do you see my point? Go away. So now we need to draw an arrow. What do we know about vectors? Well, everything, including they don't bend, they have to be straight, they have only one arrowhead, and it has to be tangent, and it has to point in a direction provided by the line. So that's supposed to be the magnetic field vector at this point from this wire. Now, we don't really have to draw circles every single time because there is a shortcut. If we remember from geometry, if I draw a radius of that circle, a line from the center of a circle to this point, it has to be perpendicular to the tangent line. So this is what we always can do. And I'll be back. Maybe not. Who stole my arrow? People keep stealing stuff from me. This radius, magnetic field vector. Well, here and at any other location, magnetic field vector will be perpendicular to the radius. All we have to do is just move it in our mind. And to do that, we need to be able to imagine things. So when people say mathematics is the most important for learning physics, no, that's wrong. Memorizing, no, that's wrong. Imagining stuff. Well, we're done with wire. Oops, that was the wrong slide. All right, I will check it later. 1, 2. The wire number 2. Current is out. That's the origin. Now we know what to do. We just have to draw a radius of that imaginary circle from a wire to the location where we're measuring or calculating field. Now, magnetic field vector must be perpendicular. Technically, we have two options to choose from, still perpendicular. One option is wrong, another option is correct. Here, we should imagine briefly how we're using right-hand rule. Right-hand rule says counterclockwise, of course, again. And here, counterclockwise means like this. So, wrong choice. Now, we can move on to the third wire very briefly. The third wire has a current pointing away from you into the screen, but the location where we need to draw the vector is the same. So now, again, the radius of imaginary circle, two possible directions. One is wrong, one is correct. So, what do you think? Which is the correct direction? To the right or to the left? For this one? To the right. The thumb now must be directed into the screen, and the fingers show you clockwise direction. So this is wrong. And finally, one more time. Again, out of the screen. And out of the screen means automatically relative to us, magnetic field lines will be counterclockwise again. But we need to draw an arrow. So again, a radius, two directions, and only one is correct. Now, it's not left, it's not right, it's up. Now, of course, we just need to draw all four together. So the origin, this point, and for magnetic field vector, we use letter B, B1. Now, if I want to draw magnetic field, four magnetic field vectors, some of them might be longer, shorter. In this situation, R, 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 the distance is the same, and the current is the same, which means all magnitudes should be the same. So B1, B2, B3, yep, just checking, B4. These are four vectors, four individual vectors. To calculate the net vector, we have to apply the same procedure we've done before. B net, well, technically those are vectors, should be equal to B1 plus B2 plus B3 plus B4, which is this plus this plus this plus this equals, you gotta draw so what do you see? Sometimes some arrows cancel each other out. In this situation, what should be canceled? Up and down, B2 and B4. So the result is this plus this or this. So the direction of the net magnetic field is to the right. If we want to calculate the magnitude, it has to be, well, 2 times, let's say, B1. Yeah? 2 times, well, the current is the same. We don't really need that subscript, just and the radius, the distance. So, any questions? This example describes the strategy for any number of currents for any possible situation. So we just need to practice. So that's a picture you actually can read. Now, what do we do if we need to calculate? In this situation, the magnitudes are different, but the configuration is the same. So we just have to preserve the direction but change the magnitude. So what do we do? The origin. And first I want to see what's happening to these two currents. They provide, again, the magnetic field, which is opposite to each other, same magnitude, so just cancel it out again, and we have still B1. Actually, a little bit longer, because the first current is higher. B1 and B3. So I just reused our strategy about directions. Yeah. But now if I want to calculate the net magnetic field, we just need to add 2 magnitudes. So what do we have? Well, 4 pi times 10 to the negative 7th, and the current number 1 is 30. 2 pi, distance equals 2, plus 4 pi 10 to the negative 7th, 10, 2 pi over 2. Pi over pi, 4 over 2 times 2. So what's left is 30 plus 10, which is 40. 40 times 10 to the negative 7, 4 times 10 to the negative 6 Tesla. We could probably call it, and that would have been probably on Weber sign, micro, 4 micro Tesla. Any questions? Please. All right, no questions. Not sure if it's a good sign or a bad sign, but it is a sign. So, one more example, please. I want to stop talking for, I don't know, some time. I want you to copy the picture. I want you to draw the magnetic field due to the wire number 1, the magnetic field due to the wire number 2, the net magnetic field, which you were looking for, and then finally, this day has come. You can take your phone, use it to take a picture of your picture, and email it to me. So I would be busy late night today. So you read the problem, and every time when you do that, you only have 2 states, like anybody else. Clear understanding of what is going on, or maybe something confuses you. That's the only 2 states of mind any human being might have. A clear understanding, or something is not clear, right? If you have a clear understanding, what do you do? Just do it. What is a problem? What do you think? When we say, that's a problem, what do we mean? Well, if you've taken PY105, you know what it is. A problem is a situation when we need to do something and we don't know what and how. If we know what to do, it's not a problem. It's a task. We just do it, right? So, perfect picture. Now, please draw. You need to finish with 3 arrows. First arrow should clearly show the magnetic field vector at the origin due to wire number 1. Second arrow, second vector, should show the magnetic field due to wire number 2, where at the origin here. And then the third arrow should demonstrate the net magnetic field. This is where, well, some thinking is happening. Not much. Basically, most of the work is just searching. Where is the rule about direction of magnetic field? Not here, not here, here. That's my cell for the rule. Where is the rule for the word net here in this cell? I just need to connect those 2 together, right? As long as I start getting your pictures so far just PayPal. No, I don't need PayPal. Someone called me. If you want to talk, you can talk louder. You don't have to whisper. Talking helps. It fires up more brain cells. Everything which helps to fire up more brain cells helps. You can talk, you can gesture, you can walk. I wouldn't recommend napping unless you close your eyes to imagine things, to visualize what's happening. All right. Okay, I'm starting getting the emails. So, again, I don't usually use a picture given to me. I like to redraw it because, again, muscle movement helps to think. We have two wires, right? Number one, number two. Again, as a time-saving technique, you can just memorize. If you look at the wire with the current at U, right-hand rule automatically will give you direction for the lines counterclockwise. So you don't have to do it every time. You can just remember it. And here we have magnetic field lines number one, magnetic field lines number two. You see, they don't look differently. But here, if we want to draw a magnetic field vector, it's an arrow, it can be bent. So B1, that's current number one, that's current number two. What's supposed to be the direction for B1? How do we say it in words? Yes? You moved, so now you have to say something. What is the direction of B1? Down, you mean like this? No. Right, you're right, right. B1, B2 is down. For some reason. And now we can draw the net. This is the part where by now we shouldn't think. This is a standard procedure, tail to a head. Why is it important? Well, depending on the shape, we use different type of a geometry. And in this triangle, well, first of all, what's wrong with this picture? There is still something wrong with this picture. What do you think?
No labels?
What else is wrong with this picture? I would say even wronger than no labels. What do you think? Yes?
Your B1 should be bigger than...
It's not a big deal. Well, all right, I'm going to tell you because you know it, you just don't believe. It's too small. A good picture is a big picture always, so we just need to enlarge it. B1 indeed supposed to be slightly longer. If we do geometry, it will not affect our calculation at all, right? So B1, B2. This is the angle we would need to find if the question was about the direction. Yeah. And B net represents the hypotenuse. So this is what I'm gonna do. And what over what? B1 over B2, or B2 over B1? And I'm not going to do any numbers, you can do it. This is an exercise in net magnetic field. That would be the exercise in geometry. This is a physics class, right? Not geometry class. So, all right, I'm going to give you a minute. I'm not asking you for your pictures, but you should draw a picture anyway just for yourself. Right now, in this example, we have two wires with electric current traveling either into the screen or out of the screen. And the question is, where, if any, net magnetic field due to these wires should be equal to 0, if it's possible. Maybe it's not possible. We have solved a very similar problem with charges. A charge is a source of electrostatic field. Now we have a different source, a different field, but the problem is actually the same. So we need to apply the same type of reasoning. And every time when we read a problem, we have to make a translation from what we read from text into our understanding of what's happening, visualize, draw a picture. So, and then we have to apply the most powerful, the oldest scientific method, which is what? The most powerful, the oldest scientific method. What is it? Method of uncovering things about the nature. What do you think? Anybody? And yeah, trial and error, guess and check. So where can we guess and check? Well, again, like in the problem for charges, we technically have 9 different regions, 9 different locations to check. 1, 2, 3, 4. It beginning to failing again. 5, 6, 7, 8, 9. So, of course, some of these locations don't really make any sense to spend time on it, right? But so you should choose at least one and check it. This is for IT. Jittering again. And your witnesses, it started at 9:34. Oh, 37, yeah, 37. 37 minutes in the class time. So we can call them 1, 2, 3, 4, 5, 6, 7, 8, 9. So please, anybody, tell me which location would you want to try? Which? 5. a very reasonable choice. 4, 5, and 6 lie on the same line. Other probably wouldn't work because of the angles. So here, clockwise, counterclockwise, we call it I1, we call it I2, so that would have been B1, that would have been B2. So what do we say? Is it the right location? No. So current number 1 is higher, and we want to be farther away from the stronger source. So let's check 6. Here, what should we have? Magnetic field number 1 here still should point down, but magnetic field number 2 here should be directed up, right? Down, up. And together, at that particular location, they should cancel each other out. Well, first of all, to describe a location, we need either x coordinate or certain distance. We can say x equals 0 here. This is x equals 2. And this is just, let's say, a distance d. We can calculate that distance. And the condition we have to use is this. That only can happen at one location. And now what do we write? And what should I write for the distance from the second wire to this point? The distance from the second wire, yes?
D minus 2.
D minus 2, but that only because of my choice for D. It could have been different, but if we set D to something, we can change it. Yes? Yes?
Shouldn't X at the second wire wire is located
Yes, you're right. Thank you. So this is 0, this is negative 2, this is 2. And I still shift 0 back to this, but that will be 4 now. Thank for the lady who pays attention better than I. So that's going to be D minus 4. Yeah, thank you. Who would write this? I don't know. So, first of all, we can cancel out lots of things immediately. This constant goes away, 2 pi, and the equation is not quadratic, which is a good thing. It's much easier to solve 30 over an unknown, 20 over that unknown minus 4. You know it's Wednesday, right? I can write everything unclear except 4s. I have no idea what this was. So, 0 and 0 getting cancelled. 3d minus 12 equals 2d. D equals 12. Just check my math. 0 and 0, 2d, 3d, 12. And we assume meters. Meters. this type of work is easier than we've done before because we don't have to unsquare anything. Questions, please? Now, we saw this magnetic field generated by this electric current. Remember the demonstration? So if you have a loop, magnetic field lines inside the loop, they point through the loop one way or another. We could use the right-hand rule, like here, for example. I grab this part of the loop, and magnetic field lines here supposed to be like this, and here like this. But there is an easier right-hand rule, which probably by now it's right-hand rule number 6. If you have electric current in the loop, you can use your right hand and curl your fingers in the direction of electric current. The thumb will show you automatically the direction of magnetic field inside the loop. Outside, of course, it's going to be opposite. So, and if we want to calculate the magnetic field generated by the loop, we can do it only at the center. It changes. It's not uniform. But right here, we just have to apply this equation. And you can see the difference between an equation for the loop and for the straight wire. For the straight wire, we have a pi. For the loop, we don't have a pi. That's it. And now we can solve this problem because it is not a new problem. It has one new equation, but the problem is same old: calculate net magnetic field. And to calculate net magnetic field, we know what to do. We have to draw each individual magnetic field, look at it, calculate the net. Done. So again, please take a minute and draw the magnetic field vector of magnetic field generated by the long wire at this point. And then the magnetic field number 2 generated by electric current inside this loop at the same point. That's the most important part. The rest is just plug in numbers, calculating, done. And again, remember, we have symbols which help us to visualize and to demonstrate an important direction. That's what we call right, left, up, down. For the symbol, for the direction which we call into the screen, what do we use? Like a circle with a cross. That's into the screen. And for out of the screen, circle with a dot. Some people just use a dot or just use a cross. Doesn't really matter if you know what you mean, if you can say. And here is a case when you have to use these symbols in and out, in or out, right? Because magnetic field at point P can't be up or down, can't be right, can't be left. Again, sometimes it might be helpful to imagine that you are looking at the wire from a side, straight at it, because you know when a current travels at you, magnetic field relative to you should be counterclockwise. So you can apply this knowledge for this wire, but counterclockwise from that perspective means right here, right now, the arrow should point into the screen. You should see it. If you don't, you should practice. So that's what we, well, that's what we should use, that what symbol for magnetic field number 1. Now, magnetic field number 2, how does it point? in and out, in or out. That's where the newly learned right-hand rule might be handy, right-hand handy. So fingers should go in the direction of the current. The thumb shows magnetic field. Magnetic field number 1 plus magnetic, well, those are vectors. Number 2 is what we call the net or total magnetic field. Question? Yes or no? Does it mean that the magnitude of the net magnetic field is equal to the magnitude of the first magnetic field plus the magnitude of the second magnetic field? 30 seconds, 30 seconds to think. Choose your answer, yes or no. And please, if you think yes, raise your hand. No. Those are vectors. Those are numbers, magnitudes. I said magnitudes. I could have actually clearly shown if I used components. That would have been absolutely correct. By the way, what is the direction of the z-axis? If we calculate components relative to z-axis, we should see it. We know the x-axis, well, according to our agreement, points to the right. Y-axis points to the left. How does z-axis point? We need to remember that it's not part of the reasoning. It's a part of a memory cell. That's how x, y, and z axis is related. Well, it's a standard right-hand reference frame, x, y, z. Now, not for sale, but you can make your own. Because this also helps, you know, because I've seen many times before when people start applying right-hand rule and start moving the rule, they also start curling fingers. That's not the right-hand rule anymore. So moving and preserving directions is important, but the easiest way to do that, just have something like that for you. So, well, right now, relative to z-axis, b net z should be equal to b2 minus magnitude of b1. So z points at s. So b2 has positive component relative to the z-axis. b1 has a negative component. And that's what it means. Now we can just plug numbers in and calculate. The rest is mathematics. So why do we talk about magnetic field of a loop? Because we use it. We use it for different purposes. For example, if we have many loops coiled up together, that's what we call a solenoid. And a solenoid has important practical applications. A solenoid can generate a very strong magnetic field, strong enough to lift heavy weights. The equation tells you how we can calculate the strength of the magnetic field inside the solenoid. It's almost uniform, which is also a good thing because it's much easier to study. Now, there is magnetic field. Okay. That's how we check the presence of magnetic field. But it is not strong enough to lift this 1 kilogram weight. But we know that metals, iron including, they can amplify magnetic field by, well, iron actually by a factor of 1,000. So if I insert a core, the magnetic field now inside the solenoid will be 1,000 times stronger than it was before. And it's strong enough now to lift, to overcome force of gravity. Well, of course, people have it manufactured, built in. This is what we call electromagnet. Yeah. And so you've seen it before many, many times, at least in movies. Junkyard, yeah, a crane takes a car, then drops it. We never know if there was body inside of that car. That's what I've learned from Sopranos. So, this is the equation which tells us how to calculate magnetic field strength without a core inserted. So we just need to know the number of loops, the length of the solenoid, electric current. If we're adding a core, in that case, we need to multiply by a factor of, well, wherever it is. For iron, it's about 1,000. Permeability depends on the name. You just Google, and wherever it's like a dielectric constant, similar. And now, finally, a question to you again. What do you think about this situation? This is a loop with electric current traveling through the loop, but it's placed in the magnetic field. So we know a loop with magnetic field is acting like a magnet, and an external magnetic field should affect. The question is how. So what do you think about the net force acting from this magnetic field on this loop? Oh, I broke something again. I've got here a very strong magnet, which, as you know, can generate almost uniform magnetic field between the poles. And I do have a loop. Connected to a battery. Well, not now. But what's going to happen to the loop? And this is a time when I want to see what you're answering. Resend. And that is a question number 3. The whole distribution. Oops. I'm just waiting. I want to check one more time your answers. First of all, what is a net force? The answer to this question doesn't require thinking. It requires taking the information from a memory cell. It's the sum of all forces acting on an object. How many forces are acting on this loop? Well, we can break it down into 4 individual wires. So you calculate individual forces and add them up. That's the strategy. But in order to see those forces, you have to apply the right-hand rule number 2, I think, for the direction of a force acting on a wire from magnetic field 4 times. So we gotta call them like 1, 2, 3, 4. Seven wins, which is very good because that is exactly the right answer. So here, current, field, force points into the screen. Now what we can do, again, current, how would it, okay, field, but now current is not, I can't use my right hand for the wire number 2, can I? No, I can't. What does it mean? All right, let's try left. If current is to the left, fingers don't show magnetic field. If fingers show magnetic field, index finger doesn't show. Can I use my left hand? No. What do we do? What conclusion should we make? If we can't use the right hand, we don't have to use, we don't use left hand for the current, but still we could try and it still doesn't work. What conclusion should we make? We just said it, we can't use the right hand. What conclusion we make from that statement? It's a situation when we cannot apply it. It's not applicable. Why? Well, because the right-hand rule only can be applied when all directions are perpendicular. Here we have a current and magnetic field parallel to each other. What is the angle between these vectors? 0, 0. Now remember, the equation for the Ampere's force magnitude actually has 4 variables, I, L, B, sine theta. This is how we used to write it, I perpendicular LB. That's why there is no sign, because it's hidden. But if you write it explicitly, what does it give us for the magnitude of the second force? 0. Sine 0 is 0. 0. And actually immediately number 4. The angle will be 180 degrees, but still sine of 180 is 0. And here we switch the direction of the current, which means we have to switch the direction of the force. So we have one arrow pointing away, plus 0, another arrow out, plus 0 again, and those cancel each other out. There is no net force acting on this loop, and this answer doesn't depend on the shape. It could be circular, triangular, or any other shape. As long as a loop is placed in a uniform magnetic field, net torque, net force will be 0, but net torque will not be 0. It will spin. Net force is 0, but remember mechanics? Remember torques? All I need is a current through this loop. and the third hand. Oh, see? When I connect the battery, it turns. Now, if I place it like this initially, and I connect the battery, nothing happens. If there is a certain angle, it go away. It still turns. So there is orientation when we observe strong torque, nothing, and something in between. Actually, how do we use this? Well, to finish with this card forever, this is how. Electric motor. We applying a magnetic field to many loops with some special engineering, but in the end we can transfer chemical energy which stored inside this battery into mechanical energy which we can use. Even if we have only one loop, it's gonna work. One loop, see? Many loops, one loop, battery, connect, nothing. What's missing? What is missing? Can't hear you? Exactly, I need the magnet. It has to be in the magnetic field. No magnetic field, nothing should happen. So we need magnet, north, south, that's it. Because this thing, the rotor, has to be designed in a special way, otherwise it would be just oscillating, wobbling back and forth, back and forth. We need to, when it makes a half of a revolution, at least a half of a revolution, we have to switch the direction of the current to keep it running in the same direction. So that's why we study this thing, motors, yeah, Tesla cars, I mean, that's how they move, batteries and motors. So we have two different situations. A situation number one, when a torque reaches maximum, and the situation number two, when torque is zero. On the left, a situation when torque is maximum. Now, the equation comes in a minute, but I just want to say sometimes it's very handy, very useful to look at the same loop, to look at the same situation from different perspective. So if this is, let's say, top view, what you see from above, it will be seen in the future that sometimes it's convenient to imagine what would you see if you would look side view. If you know, so first of all, side view. This is the loop, magnetic field. Now you have to imagine that you're floating above and look down. What would you see? Only this. So you wouldn't see the loop. You would only see one side of it. But sometimes that's exactly what you need to see. This is the top side. In this side, electric current travels to the right. Here, electric current travels away from you, then toward you, and below this, electric current will be traveling to the left. And magnetic field still points to the right. And this gives maximum torque, which actually easy to calculate because we've done it before. if we choose this axis of rotation, we need to calculate force, which is ILB, and we need to multiply by the lever arm, which is this. Well, let's say it. This is what I called L. So this is what I should call something different. Let's say S. So that should be a half of S. And because we have another force like that, we have to multiply by 2. And IBLS tells us IBA, length times width for the rectangular shape is equal to the area. But this equation actually doesn't depend on the shape of the loop. Could have been circle, could have been trapezoid, anything. As long as magnetic field is uniform, and as long as the loop is in the plane of magnetic field, this will be the torque acting on it. Here it will be 0. So in this, in F net force is 0 in both cases. But in the second case, net torque is also 0. And of course now, first of all, we need a way to describe the mutual orientation between the loop and magnetic field, because it matters. And people could have used the angle between the loop and magnetic field. So magnetic field, loop, I can turn loop or change magnetic field. So there is always certain angle from 90 to 0. But historically and from other reasons, people don't use the angle between the loop and the field. They use the angle between the vector which is perpendicular to the loop and the field. This vector has a name, and you know that name because we know perpendicular always means normal. So to demonstrate the mutual orientation between the loop and magnetic field, we don't use the loop, we use normal to the loop. And this angle might differ. And here, if I draw the normal, so it should be a vector pointing like this. And this angle between the normal and magnetic field is 90. And here, if I draw that normal, this is my loop, and you don't see it because all you can see is just this side of it. But the normal, which is perpendicular to it, parallel to magnetic field. And there is another name for this vector. If we set its magnitude to area, we call it area vector. So now, of course, well, that's an official definition. An area vector is a vector which is perpendicular to the loop, which has magnitude equal to the area of the loop, and the last condition sometimes useful, sometimes not. When we know the direction of the current in the loop, we use right hand rule number 8 to relate the direction of the current in the loop and area vector. If we curve fingers in the direction of the loop, the thumb shows the direction of the area vector, but that only works when we know. If we don't know, we just pick any direction and see how it works out. For example, if the current alternates in time. But for DC current, we always can use this rule. And now we can write the general equation for a torque acting from a uniform magnetic field on a single loop. Again, these are extreme situations. And for anything in between, I'm going to reveal you the equation. Of course, we're going to use an angle between the magnetic field and the area vector. And when this angle is 90 degrees, sine of 90 is 1, the torque reaches maximum value. When this angle is 0 or 180, the torque is 0. So magnetic field, area vector, maximum torque. Magnetic field, area vector, 0. You saw that magnetic field makes a loop turn. So again, that's not a rule, that's a mnemonic device. If we let a loop move from rest, that's how it wants to be. Because it always wants to experience the least torque possible, which is 0. So that's how we always can see what should be happening if we let it go. And now, this. All right. And now, this. I stole this phrase from John Oliver, if you know who it is. If you don't know, check it out. Especially if you're watching Game of Thrones, because in that case you should have HBO already. I haven't seen any episode. I'm going to retire eventually, so I'm saving. But if you have already HBO, watch Bill Maher and John Oliver. I wish I could give you extra credit for that. I can't. But this is the question related to the previous slide. How would it move? An area vector represented by the red arrow, and the long blue arrow represents magnetic field. And these are possible answers for the torque. And now you got to go back in time. Lecture 14, EY105, torque. Well, first of all, whenever we have two directions, two arrows, we can't say anything about anything until we redraw the picture. How do we redraw the picture depends on the question. If we need to add two vectors, we have to use a tail to a head rule. If we need to measure angle or see mutual orientation, we have to redraw from the same point. They must have the same initial point. So now, if I draw vector A and vector B, that's the angle. That is the angle theta, which we have to use in this equation. And we couldn't see it until we have this picture drawn correctly like this. But now we also can say, according to the rule, how should, loop move? Do you see the loop? Can you imagine that you see it? Kind of, yeah. Well, I see the loop. Because it has to be perpendicular to the area vector. And this area vector is supposed to be closing as fast as possible using shortest path, smallest angle. And so the whole loop would be moving like this, actually speeding up, technically. And it wouldn't stop here. Without any friction, it would keep going, but now after that it would be slowing down, reach maximum, then back and forth, back and forth. That's how electric clock might work. And right now, for this particular snapshot, for this particular photograph, this direction of the motion we call clockwise. Clockwise motion, we can say angular velocity is clockwise. And for this particular motion, we also had the right-hand rule. I think that was the first one. The direction of the motion, the direction of the angular velocity, we called it into the screen. And that's the answer, number 5. How do I know the torque points that way? I forgot to mention. If it's starting moving, it's speeding up. If it's speeding up, angular acceleration and angular velocity point in the same direction. But again, net torque and angular acceleration are related by the Newton's second law for rotational motion. And there is only one torque here. So they all should, for this particular instant, have the same direction. Just a review of right-hand rules. And now we can solve a particular problem, which is very straightforward, so don't read it, just listen to me. A flat, so it means not bent, has 25 loops. So in a uniform magnetic field, the plane is parallel to the direction of the field. That's a very important statement. As we know, the direction matters. So magnetic field should be like this. The dimensions, oh shoot, it's not circular. I'm giving you time to draw your own picture. Use it. So magnetic field. And dimensions. 15 centimeters perpendicular to field lines. 15 centimeters. 12 centimeters parallel to field lines. It is very important to read literally what's happening. Torque is equal to 5.4 Newton times meter. That's the maximum value. We know right now that if I draw the area vector, that angle will be 90 degrees, and torque, magnitude of torque equals I B A sine theta. So sine of 90 equals 1, that's the maximum value. But now we need to use this to solve it for electric current. Electric current is supposed to be equal to torque over this and this. Now, total torque, of course, is the resultant of torque acting on each individual loop. So it should be the number so actually that's what we should do. 5.4 divided by the number, that gives the torque acting on a single loop, and that should be divided by magnetic fields strength, which is 0.2. And now area. The only tricky about area, we need use meters. So 0.15 times 0.12, 5.4 actually, 25, 0.2, 0.15, 0.12. So the bottom point is decimal point, the middle point is multiplication. That's supposed to be amps. You should calculate it and tell me. 60? Thank you. As you will know very well by now, if this is a wrong number, that's her fault. Next question is a little bit trickier. What will be the magnitude? Who wrote that? Of the torque. What will be the magnitude of the torque if we turn the loop by 30 degrees? So we need to change the orientation. This is the maximum orientation. Yeah. So that's the initial situation. B, loop, area vector, torque equals maximum value, and that is 60 Newton times a meter. The new orientation happens when we turn the loop by the 30 degrees. So that's the original direction. We turn it by 30. Which direction doesn't affect the magnitude? So let's say we make it closer. This is the new direction of the area vector. This is the new orientation of the loop. This is how we turn it by 30 degrees. Theta equals 30 degrees. That's the same magnetic field, which is 0.2. And my torque now should be equal to maximum value times the sine of theta. That's how we used to write it before, remember? So now, I think it might be my last question to you today. New torque equals 60 times sine 30 degrees. Yes, it is a correct way to calculate. No, it is wrong way to calculate. Make your mind, please. If you think yes, it is a correct way to calculate the new torque, please raise your hand. If you think no, it is a wrong way to calculate the new torque, please raise your hand. All right, now just please you raise hand. Please raise your hand. Wrong. What is wrong with that? What do you think? What do you think? Guess. What's wrong with that? Well, I just said it's wrong. And now this number, this calculation has only two numbers. 60 represents the maximum torque. All right, did you check the number? Is it 60? Did you check the number? Did anybody check the number? Is it 60? Why should I do all the work? Please, someone check the number. I don't know. I just want to make sure. 60, perfect. So if this is the correct number, what might be wrong? Current, affects 60, if 60 is a correct number, that means, No. It's empty. What number should I write here? 5.4 with a perfect 4. Still wrong. I made 2 mistakes. I didn't know that. Now I know. Thank you. But there's another mistake. What is that? We fixed 1 mistake. What's left? Angle. How should it be measured? It has to be measured according to a definition. We don't think about definitions. We know them and we apply them. The angle must be measured between magnetic field and area vector. So we have to look at magnetic field direction, area vector direction, and measure the angle between these 2 directions. Is it 30? No. That's 60. That's 60 I meant. So the correct calculation is supposed to be 5.4, which is torque, times sine of 60, which is square root of 3 over 2. Please, tell me the number. 4.67 and Newton times the meter. So of course it should be less than maximum. When we turn away from maximum, we decrease torque gradually to 0. So this is something in between. Any questions? Do you have a question? Do you have a question? No questions? In that case, we're done for today. Thank you very much. Good morning. Let me just think for a moment. I'm gonna switch some stuff because I'm not gonna use this anymore. You can put it away here. But I'm gonna need my arrows. I'm gonna need this. Oh, shoot. I'm gonna need my magnet. I'm gonna need this. I'm gonna need this. I'm gonna need this. My arrows. So I am done with this card. Yeah. No, let's keep it here for now. Yes, questions? I changed your. Do you have the access?
No.
Did you check? Did you try different browser? I sent